Hello FEA guys, welcome to my YouTube channel. My name is Vivek Varkal. So this is my first YouTube video. In this video I am going to talk about introduction and we'll try to understand FEM algebraic equations through solid mechanics approach. Okay, so without further delay, let's dive into the topic. Okay, so what is FEM? So FEM is a numerical method to solve partial differential equations. Okay. So further going forward, you will understand this definition more clearly and better. For now, it's a numerical method to solve partial differential equation, and this partial differential equation PDE represents particular physics. Okay, this physics can be electromagnetics, fluid dynamics, heat transfer physics, or in our case it's solid mechanics. Okay, so we are going to talk about structural mechanics or solid mechanics point of view. Okay, so with FEM what we can do. Okay, so what we want to do, we want to find the relationship between displacement and force, right? So since we are talking about solid mechanics, so these are the main quantities of interest, right? We want to find the displacement and uh, force relationship. Okay, so this is my displacement and here is the force, and I want to find the displacement relationship using FEM. Okay, so if it is a simple structure, for example, if it is a simple structure like simple spring, okay, for example something like this. Okay, the spring is applied some force, external force F. Generally spring stiffness K or spring constant is known. Okay, and let's take this spring is constant at 1 L. So we want to find the displacement of this spring. So for spring, Kf is equal to K into U. This is a known. Okay, so we can easily find the displacement using this relationship. Okay, uh, so but real structures are not as simple as a spring. Okay, if even if we take a very simple structure like bar or bar member or truss member. Okay, when we apply the force here, okay, the known quantities are area, Young's modulus and length, right? These are the known things, and we want to find the displacement for this bar. Okay, uh, so the relationship which you, which is F and U, this relationship is not known. Okay, okay, so that relationship we want to find using FEM. Uh, so generally, okay, uh, generally this relationship is not so direct. Okay, though it looks further, if you see, you will see that there is a direct relationship between displacement and force. Uh, it looks direct, but it is not direct. Generally, it is something like this. Okay, if I denote displacement as U and force F. Okay, from displacement we can find the strain. Okay, using strain displacement relation, we know that uh, from strain we can find the stress. Okay, using stress strain relation, and from stress we can easily find the force, which is force is nothing but stress into area. Okay, or in a reverse order, if F is known, okay, we can find the stress. From stress we can find strain, and from strain we can find the U displacement. Okay, so it is both ways. So it is something, it goes something in this way. Okay, though it looks direct relationship. Okay. Okay, so now let's try to understand FEM equations through 1D example. Okay. So why 1D example? It is very easy to understand anything, any concept with the 1D, right? Further, I mean, if you are clear in your fundamentals, if you understood from a 1D perspective, you can easily then expand or extend your understanding through 2D and 3D. So it is very important that on the conceptual understanding we get through a 1D example. Okay, so we'll try to understand FEA equations through 1D example. Okay, so let's take 1D element. Okay, so okay, before that there is one more thing that need to be explained. Okay. Okay. So there are two types of dimensions in FEM. Okay, one is element dimension, other is dimensions with respect to space. Okay, so for example, element dimensions, if I take example like this line element. Okay, so it is a 1D. So this element dimension is 1D because it's a line element. So element can have two dimensions as well. Okay, for example, quad and tria element. So these are 2D elements. Okay, similarly 3D elements, hex and tetra. Okay, in terms of space, there is a 1D space. Okay, if I take a 1D space, and it will have only x coordinate, right? So this 1D element, this 1D line element is positioned into 1D space. Okay, it will have only x coordinate. If I say 2D space, which will have x and y coordinates, so this line element can lie in 2D space. Okay, and it can be represented with xy coordinates. Similarly, 3D space. Okay, the line element can be in 3D space as well. Okay, xyz coordinates. Okay, so similarly, the line element in 1D, 2D or 3D space, in the same way, 2D element can be in 2D space or 3D space. 2D element cannot be fitted into 1D space, right? So 2D element can be in 1D space or 2D, 2D space or 3D space. Okay, and 1D element can be in 1D, 2D or 3D space. So what we are talking here, 1D element. Okay, or 1D example, we are saying 1D element, which is line element, 1D element in 1D space. Okay, so let's take a 1D element. Okay, uh, truss or bar element. Previously we have seen this bar member. Okay, this structural member. Okay, so we can represent that structural member as truss or bar finite element. Okay, so what is that known for this element? So since this is a 1D element, other two dimensions of this structural member is represented by cross section dimensions, right? So A is known, length is known, and material of this structure is known. So E, Young's modulus. Okay. um, so we will apply some force F here. We want to find the displacement. Okay. That is what our problem definition. We want to find the relationship between force and displacement. Okay. Okay. So we'll let's say white color only. Okay. So we know the stress and strain relationship, right? Okay. Sigma is equal to E epsilon. Okay. So sigma I can write it as a, if I further derive, sigma is nothing but force divided by area is equal to Young's modulus E, and strain is nothing but okay, I want to find the U displacement. Okay, I will denote it as a small u. So strain is nothing but displacement divided by original length. Okay, so I did nothing. There is a stress strain relationship. I since I have A L E and F. Okay, I just converted them into in terms of F A E L. Okay, so I can write it as F is equal to A E by L into U. Okay, so what is this? Okay, uh, there is a relationship between F and U. Okay, which is nothing but A by L. Okay, so I can say this is this relationship. We can say it's a K, right? So in other terms, the bar element, okay, bar or truss element, which represented that structure bar, sorry, some structure. Okay, that bar element can be represented into equivalent spring, right? We can say that. Okay, and this is nothing but this is a big idea. This is big idea in FEM. What is that? We can represent the member, structural member, uh, which is represented by bar element. We can represent bar element of AEL into equivalent spring of K. Okay, so this is a big idea in FEM or FEA. Okay, both are same. FEM is finite element method is more used in universities, whereas FEA is a more popular word in industries. Okay, so we have no we have achieved our goal. Okay, that we wanted to find the relationship between force and displacement. Okay, and if I just rewrite it, okay, F is nothing. Okay, I'll rewrite. Okay, F is equal to K into K effective. Okay, since this the K which we used was for spring constant, so I will use K effective into U. Okay, and where K effective is nothing but AE by L. Okay, so this is a big idea that any element, any finite element, okay, can be represented into equivalent spring. and we have to just find that equivalent spring stiffness. Okay, that is nothing but K effective. Okay, and by doing this, by doing this that 1D 1D element to 1D spring, okay, we are not losing anything conceptually. We are not losing anything conceptually, right? We are maintaining the behavior of structure or element. Okay, so we can represent 1D finite element as 1D spring, and we have to just find that effective spring constant, or in another term spring stiffness, okay, or element stiffness.